All right, we just did a lot of work to prove the existence part of the division algorithm. Now we're going to go for the uniqueness part of the division algorithm proof. And just so you know, this one's not going to be quite as rough as the other one. So if the other one seemed a little bit tough to bear, this one's going to be a little better. All right, so we're first going to review the statement of the division algorithm so we can remember what we're proving. We're going to outline the uniqueness part of the division algorithm proof. We're not going to give a formal proof, but give you the ideas so you can sort of see how the formal proof is. If you want an actual formal proof, those are posted up with the in-class activities. All right, so to remind you what the theorem says, let a and b be in integers with a positive, then there exists unique q and r such that b is equal to aq plus r. In other words, q and r are quotients, is a quotient and remainder, and r is between 0 and a minus 1. So the uniqueness part of it is to show that for every division problem with integers, there is precisely one remainder and precisely one quotient that makes the remainder between 0 and a minus 1. So we're going to prove this by contradiction, and the first thing we're going to have to do is state precisely what it means, what it would mean for that theorem to be false. Well, if the quotient and remainder aren't unique, then that means there's more than one of them. So there are two quotient remainder pairs. And so we're going to assume that there are two quotient remainder pairs and show a contradiction. So we're going to assume that we have q1, r1, that's the first set of quotient remainders, q2, r2, that's the second set, such that, well, what does it mean to be a quotient remainder pair? B is equal to aq1 plus r1 for the first one. For the second one, it means that b is equal to aq2 plus r2. The first remainder, r1, is between 0 and a minus 1. And guess what? The second remainder, r2, is also between 0 and a minus 1. And I do want to point out that the two quotient remainder pairs being different doesn't mean that both the quotient and the remainder have to be different. It means that at least one of them has to be different. Either the quotients have to be different, or the remainders have to be different, or both. All right, so let's see where to start. Well, let's start with those first two equations. B equals aq1 plus r1. B equals aq2 plus r2. And the nice thing about both of those equations is both of those expressions on the right-hand side of those equations, they're both equal to b, which means they're both equal to each other. So aq1 plus r1 is equal to aq2 plus r2. We're going to do a little bit of algebra to make that one a little bit nicer to deal with. We're going to move all the r's to the left and all the q's to the right. So we get r1 minus r2 on the left, aq2 minus aq1 on the right. And if you look on the right, you can notice that a is a common factor between those two terms. So we're going to go ahead and factor that out. So now we're going to look at the inequality r1 is between 0 and a minus 1, see what we can do with that. Well, we actually have another inequality, right? R2 is also between 0 and a minus 1. And what we want to do is somehow connect that to the previous equation for r1 minus r2. So in order to do that, what we're going to do is, let me see, we've already got something about r1, and we want to minus r2. So we're going to take that second inequality and multiply all sides of that inequality by negative 1. And when we do that, we got to remember, whenever we multiply by a negative number, that flips the inequalities. So we're going to get 0 is greater than or equal to negative r2, greater than or equal to 1 minus a. And remember, we get 1 minus a because that's what you get when you multiply a minus 1 by negative 1. And then we're going to turn that around so they're all less than or equal to instead of greater than or equal to. And now we have two sets of inequalities, and we're going to add each side of those together. So the left-hand side, when we add that, we get 1 minus a. When we take r1 plus a negative r2, we get r1 minus r2, which was exactly what we were looking for. And when we take a minus 1 and add 0 to it, we get a minus 1. So that r1 minus r2 in the equation above all this inequality stuff is between 1 minus a and a minus 1. And actually that 1 minus a, I don't like it, the 1 minus a. I want to write that in the form negative the quantity a minus 1, so you can see that the left-hand side of that inequality is just the negative of what you have on the right-hand side. All right, so remember, we have r1 minus r2 is equal to a times q2 minus q1. And we factored out that a, and that tells us that, well, it tells us a couple things. Remember, we also have r1 minus r2 is between negative a minus 1 and regular old a minus 1. But if you look at that left-hand side equation, that tells us that a divides evenly into r1 minus r2. r1 minus r2 is equal to a times the integer q2 minus q1. That means a divides evenly into it. And of course, we still have r1 minus r2 is between negative a minus 1 and a minus 1. So the question I'm going to ask now is, what are the multiples of a between negative a minus 1 and a minus 1? Because whatever it is, it's one of them is going to be r1 minus r2, right? r1 minus r2 is between negative a minus 1 and positive a minus 1, and it's also a multiple of a. So I'm going to see what possible multiples of a that r1 minus r2 could possibly be. Well, one possibility is it could be a times 0. And if that's the case, then we get r1 minus r2 is equal to 0. If we move the r2 to the other side, that one's okay, right? Being 0 is certainly between negative a minus 1 and positive a minus 1. So that one's okay. What if r1 minus r2 is equal to a times k, which we're assuming it is, but k is a positive number? Well, what kind of multiples do we get? We're going to get 1 times a, 2 times a, 3 times a, 4 times a. Remembering that a is a positive number, the smallest that could possibly be is just plain old a. It's either going to be a or a number bigger like 2a, 3a, 4a, etc. Right? But you know what? That is not okay. r1 minus r2, we've already established, is between negative a minus 1 and positive a minus 1, which means it can't be bigger than a minus 1. So that one's not okay. But remember, what we're saying is not okay is not just that r1 minus r2 is greater than or equal to a. If you look at where that came from, it's not okay for k to be greater than 0. So k equals 0 is okay. All positive numbers k, not okay. Lots of k's in that sentence. All right, so now I want to look at the rest of the integers, r1 minus r2 equals a times k, where k is a negative number. So that's negative k, negative 2k, negative 3k, negative 4k. I'm sorry, negative a, negative 2a, negative 3a, negative 4a, etc. Now, those are all going to be negative numbers because a is positive. And so now I'm going to use the same kind of reasoning. The biggest possible number that those multiples of a can be is negative a, right? Because negative 2a is smaller, negative 3a is smaller than that, and so on. So that says that r1 minus r2 is less than or equal to negative a. Well, guess what? That's not okay either. Remember that r1 minus r2 is at the smallest negative quantity a minus 1. Negative a is smaller than that, so that's not okay. So what has happened here, right? All the 0 is okay for k. The positive numbers are not okay. The negative numbers also not okay. That means the only one that is okay is r1 minus r2 equals 0. But if we have that equation, we get r1 equals r2. Pretty nice, huh? All right, so we've proved now that the remainder is unique, right? We can only have one possible remainder. Now it's actually a pretty short trip to proving that the quotient is also unique. All right, so here's our story so far, right? R1 is equal to R2, which we're going to call R because they're both the same thing. That tells us, well, we know that B is equal to AQ1 plus R1. R1 is equal to R, so we have B equal to AQ1 plus R. B is equal to AQ2 plus R2. Remember, R2 is also equal to R, so that gives us B equals AQ2 plus R. Again, we're going to set those two expressions for B equal to one another. AQ1 plus R equals AQ2 plus R. We're going to subtract R from both sides to get AQ1 equals AQ2. We're going to move that AQ2 over to the left-hand side and factor out the A. And so let's see what we have, right? We have two things multiplied together to give us 0. A times Q minus 1 minus, or Q1 minus Q2 equals 0. And we proved, or you proved on your homework, that if you have two integers that are multiplied together to give you 0, that means one of them is 0. So either A equals 0 or Q1 minus Q2 is equal to 0. Well, we know that A is not equal to 0 because A is positive. That was part of the assumptions of our theorem. So A cannot be equal to 0. That leaves us the only choice, since A is greater than 0, that Q1 minus Q2 is equal to 0. And then that tells us that Q1 is equal to Q2. So, in summary, we assume that we had two quotient remainder pairs, right? Namely Q1 and R1 and Q2 and R2. We proved that R1 is equal to R2 and Q1 is equal to Q2, which meant that we only really had one quotient remainder pair after all. That means our two quotient remainder pairs were really one quotient remainder pair, And our conclusion was that the quotient and remainder are unique, which proves the theorem. Done. Well, that finishes up that one for the division algorithm. Now I encourage you to go on to the next set of in-class activities and videos.